In this video, I'll be presenting the process for finding the percent yield in a stoichiometry problem. To understand what the percent yield is, we have to get down to a few core understandings. The first thing is that when humans are going through and trying to produce some sort of product through a chemical reaction, we don't actually make as much of the product as we theoretically could have made. All right, and the reason is because humans make mistakes. We might measure out the wrong amount. We might heat it incorrectly. There are all sorts of things that can go wrong in a chemical reaction, and so we just won't produce as much of the product as we would like. Additionally, a lot of times when you're doing a chemical reaction, there are unintended sort of side reactions that occur. I use the example of combustion to try and illustrate this point. So generally speaking, we say in a combustion reaction that you make carbon dioxide and water. However, sometimes if there's not enough of a source of oxygen available, instead of making carbon dioxide and water, we undergo what's called incomplete combustion, and it creates carbon monoxide and water. And so that is a side reaction that takes place along with the normal reaction, and we get these unintended byproducts that we create. All right, and so for both of these reasons, we don't ever create in a chemical reaction how much we think we might theoretically be able to make. All right, which gets me to some other vocabulary here. The actual yield in a chemical reaction is the amount of a product that we actually make. So if you're trying to make a product in the lab, the amount that you actually are able to make and collect is called the actual yield. All right, the theoretical yield is the amount of a product that we would be able to make if everything was perfect. So starting with the reactants that we start with, the theoretical yield is that maximum amount we can make if we did a really perfect job of doing it. To calculate the percent yield, we take the actual yield and we divide it by the theoretical yield and we multiply it by 100. Now it says this can never be greater than 100%, and it's asking you why that's the case. Well, if you think about it, the theoretical yield should be the maximum you can make. And if you're taking the actual yield divided by the theoretical yield, you should always be taking a small number divided by a relatively larger number. Your actual yield shouldn't be more than your theoretical yield because that would mean that you made more than the maximum possible amount that you could make. And so if you're ever doing one of these problems and you end up with a actual yield that's larger than your theoretical yield, or if you end up with a percent yield that's greater than 100%, then something has gone wrong and you should go back and check your work. So some of this might not make the most sense, but what I'm going to do is I'm going to go through an example problem here, and hopefully after I've gone through this example problem, things will make a little bit more sense. So we've got some different steps here. The first steps, generally speaking, are to go through the stoichiometry problem like normal, all right? Identify what the theoretical yield is. You get that from the stoichiometry problem, all right? And then we take actual yield divided by theoretical yield, and we multiply by 100. So reading this first practice problem, it's actually quite a doozy. All right, so I'm giving you the amount of potassium and the amount of oxygen in a reaction that creates K2O. The first thing I'm going to do actually is to balance this chemical equation. We've got potassium, which is K, and oxygen, which is O2, and then it's making K2O, potassium oxide. In this reaction then, we've got to balance it. The first thing I'll do to balance the oxygens, I put a 2 here in front of the K2O, and then the oxygens are balanced. Then I would need a 4 in front of the K to get everything balanced there. All right, and this is what's happening here. Now I've given you an amount of K, and I've given you an amount of O2, which means I'm giving you a mass for two different reactions. If I give you two different masses for the reactants, that should signal to you that we're dealing with a limiting reactant problem, which means I don't know if I'm going to run out of potassium first or oxygen first, which means I need to do the stoichiometry problem twice and figure out what my limiting reactant is so I can figure out how much I'm actually supposed to make. The end of this problem says that in the lab, you're able to collect 7.36 grams of K2O, all right? And so the amount, this last mass, this mass of your product that you're given, it's important that you identify that this is your actual yield. All right, it's how much you are actually able to collect at the end. So it's called the actual yield. And We'll use that in the last step of this problem, but just keep in mind that it's there. And so as I said, what we're going to do next is we're going to do a limiting reactant problem. In order to do that, we have to actually have some masses here. We have to have the masses of each of the reactants because we have to get from grams to moles, and then we need the mass of the product because we're going to get from moles to grams for that product. So if you look them up in the periodic table, you should get the following masses. K has a mass of 39.10 grams. O2 has a mass of 32.00 grams per mole. All right, and K2O, that has a mass of 94.20 grams in 1 mole. All right, so we will use all of those numbers in this stoichiometry problem. So what we start here with, limiting reactant problem, I'm just going to start with the amount of one of the reactants. We have 6.92 grams of potassium, so I start 6.92 grams of potassium. Then I need to get out of grams of potassium and into moles of potassium. I use the molar mass. I know that there are 39.10 grams of potassium in 1 mole of potassium. All right, and then in the next step, I need to go from moles of potassium to moles of my product. I use the mole ratio, which comes from the coefficient of the chemical equation. So we know that we have 4 moles of potassium, because that's the coefficient on potassium, for every 2 moles of K2O. Then I need to get out of moles of K2O and into mass of K2O. And so I know that for every 1 mole of K2O, using my molar mass, that I have 94.20 grams of K2O. Going through and doing that problem, I get 8.34 grams of K2O, and that is rounded to the appropriate number of sig figs. Then I need to start with my other reactant and see how much K2O I can make based on how much oxygen I have. I start with 4.28 grams of oxygen. All right, and then I want to convert from grams of oxygen to moles, so I'm going to use the molar mass. There are 32.00 grams of O2 in 1 mole of O2. All right, and then moles to moles, so I'm going to convert from moles of O2 to moles of K2O. For every 1 mole of O2, there are 2 moles of K2O. And then moles of K2O to grams of K2O, I know using the molar mass that every 1 mole of K2O has a mass of 94.20 grams of K2O. If you go through and calculate that, you get a mass of 25.2 grams of K2O. All right, this is a limiting reactant problem again, so thinking about what this means is we have enough potassium to make 8.34 grams of K2O, and we have enough oxygen to make 25.2 grams of K2O. What this means is we're going to run out of potassium first. Once we create 8.34 grams of K2O, we are out of potassium, and the reaction can't go on any further. And so this reaction here on the bottom does not happen, all right, because we run out of potassium first. And so in the end, we only get 8.34 grams of K2O. This is the end of the stoichiometry part of this. This is called our theoretical yield. All right, so the end product of that stoichiometry problem is determining the theoretical yield. As the last step, we're going to find the percent yield. We know that percent yield equals the actual yield over the theoretical yield. times 100. And remember back at the beginning of this problem, we were given 7.36 grams of K2O. That's how much we actually produced. So that's our actual yield, 7.36 grams, divided by our theoretical yield, 8.34 grams, times 100. Sig figs here, the times 100 is only getting us from a decimal to a percent, so that times 100 is not counted in the sig figs. We have 3 sig figs over 3 sig figs. Our answer should have 3. So you end up here with 88.2%. Okay, that is your percent yield. Okay, I will do one more example of this process. So it says determine the percent yield for a reaction between 3.74 grams of sodium and excess O2. And then in this lab, 4.81 grams of Na2O was recovered. So this is undergoing a similar reaction to what we had seen before. We've got sodium, in this case, reacting with oxygen and is producing Na2O. All right. Because it's basically the same reaction as the one up above, except it's got sodium instead of potassium. It should look pretty familiar. We end up with just a 2 as a coefficient there and a 4 as a coefficient there. All right. And then I'm going to identify something in this problem which is a little bit different from the last one. In this problem, if you read, it gives you the mass of sodium, and then it tells you that there's excess O2. This word excess here is actually one of your favorite, it's going to be one of your favorite words here in this process of calculating the theoretical yield, because excess O2 means that this is actually not a limiting reactant problem. We know which, sorry, it's not a limiting reactant problem. We know which reactant is limiting. In this case, we have a limited amount of sodium and excess O2. So instead of having to do 2 stoichiometry problems like we did on the last one, because it says we have excess O2, we just have to convert from grams of sodium to grams of Na2O. Hopefully you can identify that this 4.81 grams of Na2O that it says here at the end, that is the actual yield. Again, that's what we actually recover. So I'm going to go through and quickly do this conversion problem. Again, we need a couple molar masses on this one. I need the mass of Na because I have to go from grams to moles for that. So that's 22.99. Okay, I don't actually need the mass for O2 because I'm not using that reactant in this one, but I do need to know the mass of Na2O. And if you calculate that from the periodic table, you should get 61.98. So I'm going to go through here and do that conversion. We start off with the amount of sodium that they give us here, so 3.74 grams of sodium. We need to go from grams to moles for sodium, so it's 22.99 grams of sodium in 1 mole of sodium. And then we need to go from moles of sodium to moles of Na2O. So there are 4 moles of sodium for every 2 moles of Na2O. And then we're going to go from moles of Na2O to grams of Na2O using the molar mass. So we know for every 1 mole of Na2O that we end up having 61.98 grams of Na2O. Go ahead and do that calculation, and you should hopefully get 5.04 grams of Na2O. Now this here, again, the result of your stoichiometry problem, that is the amount that we could make, the theoretical maximum that we could make starting from 3.74 grams of sodium. So this is your theoretical yield. That comes from your stoichiometry problem. All right, then to get the percent yield, what we have to do is the actual divided by the theoretical times 100. So in this case, percent yield equals the actual that's given to you in the problem, 4.81, divided by the theoretical, 5.04, times 100. And if you calculate that, you should get 95.4%. All right, that is it for the examples that I will show you in this video. There is, however, a worksheet that has a few more examples, and you have your practice exam too. So make sure that you go through and check the PDF copy of the key that I put online that has the solution to those other problems. And if you're running into any problems with these, make sure that you come in and ask.